Hi everyone. So, we have been on this topic of acoustic emission testing, and in last few lectures we have seen the basic principle of this particular technique, and we have also seen the characteristics of the acoustic emission signals. And in the last class we also saw a couple of examples of acoustic emission sources. One of them was from a crack, and the other one was from a phenomena called phase transformation in metallic systems. Okay. So, today in this lecture we are going to continue on this topic and we will see the other aspects. So, first let me come back to this once again. Okay, so let me come back to this because this is the most significant feature of acoustic emissions. If you have no load, there is no emission, because acoustic emission talks about moving defects. Okay, and for the defects to move, you have to load the component of the structure. Okay. So, that means there has to be a relationship between the load and the emissions which happen inside a part. Okay. So, this relationship between the loading history and the acoustic emissions in a particular interval is given by two effects, which are known as Kaiser and Felicity effects. So, this describes the relationship between acoustic emission events and the previous load history. Since this technique is primarily to monitor the moving defects and damages like that which are active, this is primarily used for health monitoring of a part or of a system which is already in service. Okay. So, this inspection is done in a particular interval time to time. Okay. So, during a given inspection, the part will be loaded to certain extent, depending on what kind of component it is and how it is used and what is the kind of load which is being applied to the system or to the part. Okay. So, that is why there is a previous load history that also has to be considered when you talk about acoustic emission events or acoustic emission from a part when you are doing the inspection at particular intervals. Okay. So, these Kaiser and Felicity effects will tell you about that, and this is how they go. Kaiser effect describes acoustic emission events for a complete loading cycle. That means, you first load the part, unload it and then reload it, and during this whole cycle if there is any acoustic emission events, that is being described by this particular effect which is known as Kaiser effect. when the structure is first loaded to a threshold. Threshold means when it is loaded to a particular load beyond which you can expect the defect to move, okay, and then unloaded and then loaded again. Okay. So, as I said, this is about a complete loading cycle, loading, unloading and reloading. And it states that no acoustic emission is generated until the previous maximum load at which the emissions were obtained in the previous cycle is exceeded. Okay. Okay, so you are doing it, you are loading the structure and then see at what particular load the emission is occurring, and then when you reload again, you have to see whether the emissions are occurring before the previous maximum load or after the previous maximum load. Okay. So, the Kaiser effect says that there will be no acoustic emission until the previous maximum load is exceeded, and when you see that the emission events are coming only when you exceed the previous maximum load, it indicates that the structure that you are inspecting, it is still sound. Okay. There is no permanent damage to it which can compromise the safety or the function of the structure. Okay. So, that is how you get to know whether the damage is becoming detrimental for the structure or not. Okay. On the other hand, you see acoustic emission occurring before the previous maximum load, then that will indicate that some kind of damage has happened to the structure which is causing these acoustic emission events. Okay. So, emission that occur in the later loading below the previous maximum load is due to structural damage. Okay, so this is how you get to know the relationship between the acoustic emission events, the loading history, and also whether the structure has been damaged or whether the defects are been active or not. Okay. So, this second phenomena, that is occurrence of the acoustic emissions below the previous maximum load, that is known as the Felicity effect. Okay. So, the Kaiser effect is no emission before the previous maximum load, and Felicity effect states emission before the previous maximum load. Okay. So, this is about damage and no damage. Okay. No damage that is being stated by the Kaiser effect, and when the structure is damaged and you have a big source of acoustic emission, then that is being described by Felicity effect. Okay. So, as I said, this is about occurrence of acoustic emission below the previous maximum load. So, you can define a ratio which is known as the Felicity ratio, which goes like this. It is denoted as FR, and this is given by the ratio of the existing load at which you see the emission, that is P e, and the previous maximum load, which is P m. Okay. So, this immediately tells you that if FR is greater than or equal to 1, then you know that the existing load at which emission is occurring, it is either equal or greater than the previous maximum load, and as we have already seen, this means that there is no damage. Which has happened in this interval. Okay. Because as I said, this inspection is done in a particular interval. So, when you are doing the inspection during that interval, if you find that the Felicity ratio is greater than 1, then you know that during that particular interval there is no damage to the structure. Since the last inspection. Okay. And on the other hand, if it is less than 1, then you know that your existing load at which the emissions are occurring is lower than the previous maximum load. So, that would indicate that there is some damage in the structure. So, this is indicative of cumulative or permanent damage. This can also be represented graphically, as I am going to show you right now. So, this is about the load at which emissions occur. So, x axis is the load, and then you see the emissions coming out at a particular load. Okay. So, as you increase the load, you can expect the emissions also to increase like this. So, this is the loading cycle. Let us call that as A B. Okay. Then you unload it. So, B C is unloading, and then you again reload it, which is C B. Okay. Now, depending on whether you are getting emissions before B or after B, based upon that you come to know whether there is a damage or not. Okay. So, during this reloading cycle, which is C B, if you see that the curve is going like this, that means you see further emissions only after exceeding B, which is the previous maximum load, then this, as you know by now, is the Kaiser effect, which said that emissions will occur after you cross the previous maximum load, and that is what you see in this case. Okay. So, let us say during the next inspection again you do the same thing. So, this is again unloaded. So, B D is the occurrence of emissions during reloading again, okay. And then you again unload, which is D E, and then again reload, which is E D. Now, if you find something like this during reloading here, okay, in this case. So, this point F is less than D. Okay. The load at point F is less than point D. That means, the emissions are occurring before the previous maximum load, which was D in this case. Okay. So, that means, this particular phenomena here is the Felicity effect, which is about occurrence of acoustic emissions before the previous maximum load. Okay. And then, when you see this, it means that the structure is already damaged, and that is why you see a steep rise in the emissions. Although there is not much increase in the load, but you still see this part is rising almost vertically. Okay. And that is why this particular portion that you see when you have emissions before the previous maximum load, or when there is a damage in the structure, then you see this GH part which is almost like happening with no increment in the load. Okay. So, that is why this is known as load hold. That means, the load is held at a particular value. Load is not really increasing, but you still see lot of emissions coming out, which is again indicative of some kind of damage to the structure. So, this continuation of emission is indicative of unstable structure. Or unstable structural defects. Okay. So, this is how the whole thing, the Kaiser and Felicity effect can be described graphically. So, now if you talk about these different portions of this plot, then AB is loading, BC is unloading, CB is reloading. Similarly, this BD again is loading to higher loads, and then you have DE unloading and so on. Okay. And then you come to a point, particularly when the load is on the higher side, when you see that the emissions are occurring before the previous maximum load. So, that is the point F, and that is when you get to know that there is some kind of structural defects which are not stable, which is making this structure unstable and generating lot of acoustic emissions. Okay. So, this is how through these two effects you come to know about the structural damage and their relationship with the loading history. Now, we will talk about the acoustic emission signal itself, and we will see what are the signal parameters and how these parameters are used to do different things, including getting indications about defects inside the part. Okay. So, this signal which is obtained, it will be converted in terms of an electrical signal finally for the measurement system to process it and then display it. So, these mechanical vibrations or the stress waves which come out as sound waves from the sample, which are known as acoustic emissions, this will be received by the transducer and will be converted into electrical signal. Okay. So, here again as we will talk about little later, you have a piezoelectric transducer which is going to convert these mechanical vibrations or these elastic waves into an electrical signal. Okay. So, the signal what you finally see is in terms of volts, that is what I have written over here on the y axis, and then you see it as a function of time how the signal is behaving or how the signal is changing over a period of time. Okay. So, when you do acoustic emission testing, the first thing that you need to do, you need to define a threshold, and anything above this threshold only taken as a real acoustic emission signal, and below this threshold it is considered a noise. Okay. So, you may find signals like this, some may be below the threshold, then suddenly it might go up. Okay. So, you could see a signal like this. So, whatever is above this threshold which is generally user defined based upon the experience of the user or based upon the part which is being examined, this threshold is defined, and whatever you see above this threshold is considered as acoustic emission events. So, from this signal you can define certain signal parameters which can be used, as I said, for doing acoustic emission testing. First thing is counts. So, that would indicate about the strength of the acoustic emission source, and this is nothing but the number of excursions or the number of crossing you see above the threshold. So, all these peaks that you see above the threshold, okay, that is considered as counts, or if you take the numbers, that is the count. And this has to be a function of the threshold, because that is how you count it, anything above the threshold. And it is also a function of the frequency. And this would certainly depend on the magnitude of the acoustic emission source. In fact, this would indicate the magnitude of the source. And it also depends on the acoustic properties of the sample and the sensor. So, this is the first parameter that we defined, and the second parameter is known as the amplitude or the peak amplitude. Okay. So, that means the maximum signal that you have, which is this one in this case. So, this is nothing but the maximum or highest measured voltage or signal. And since we are talking about elastic waves or sound waves coming out from the sample, this amplitude is expressed in decibel. And this is directly related to the energy in the signal. So, that means higher the peak amplitude is, higher is the energy in the acoustic emission signal. Okay. So, there are few more parameters which can be derived from the signal, but today I will not have time to cover that. So, we will take it up in the next class. So, for today I am going to stop here. I will see you next time, and then we are going to discuss about rest of the things including the signal parameters. So, I will stop here today. Thank you for your attention.